Hey guys, this is Rachit Jain. My effort through this set of videos is to ensure practical understanding of simple and complex concepts with college level mathematics but with school level ease. The agenda for this video would be to understand the concept or the mathematics behind Bayes' theorem. But before that, we'll see what are independent events, what do we mean by mutual and pairwise independence, and then the total probability of any set or any event, and which would lay a path for understanding Bayes' theorem. So without any further delay, let's get into it. In the previous video, we learned about what is conditional probability, why do we call it a valid probability mapping, and what is the subtle difference between null and an impossible event. In this video, we'll jump directly into what do we mean by independent events. Let A and B belong to S, that's the sample space. The two sets A and B are said to be independent if probability of A intersection B is equals to probability of A multiplied by probability of B. As such, there is no condition on A and B except that A and B should belong to the sample space itself. From the conditional probability in the last video, we learned that if probability of B is greater than 0, we can write probability of A intersection B is equals to probability of A by A given B into probability of B, and that we called as the multiplicative law. For A and B to be independent, we know from the above equation that probability of A intersection B should be equal to probability of A into probability of B, which means that probability of A given B is equals to P of A. Since you have no effect of B happening over the occurrence of A, the probability of A given some event has occurred does not change. That is why P of A given B is equals to P of A. And this makes logical sense, right? You can see from the below Venn diagram that if A and B are independent, that does not mean that they are disjoint. So suppose A and B are disjoint, does that mean that they are independent? No. They are just disjoint sets here. On the second case, for the second case, we can say that suppose A and B are these two sets and have their individual probabilities. You can see that the math works out such that P of A intersection B is equals to P of A into P of B. Does that mean they are independent? No. If A and B are independent, then probability of A intersection B is equals to P of A into P of B. But the reverse is not true. Having understood what probability is, I am sure you must have heard the terms mutual independence and pairwise independence. So what do we actually mean by that? So suppose A, B, C are three events in the sample space, then probability of A intersection B is equals to P of A into P of B. And suppose we do that for all the three events pairwise, then that is called pairwise independence. These three equations would constitute the conditions that are necessary for three events to be pairwise independent. However, for mutual independence, we need to have P of A intersection B intersection C to be equal to the product of their individual probabilities. And all these four holding simultaneously would ensure that we have a mutual independence condition. Thus, mutual independence is a more stricter definition of independence for events. Another way to define mutual independence can be that if every finite subcollection of subsets of any set of events is independent, then the whole set of events are mutually independent. One thing to note here is that mutual independence would imply that the events are pairwise independent. However, the reverse is not true because there is an additional condition, a more stricter condition for mutual independence to happen. Let us take an example of four marbles with each of them having a particular letter written on them. Let's say those letters are AI, A1, A2, A3, and the fourth one having A1, A2, A3 together. You randomly pick a marble and let us define event EI to be alphabet AI appearing on the marble when it is picked. Assuming they are equally likely, like we used to do in school, we have that P of E1 is equals to half because probability of even means that the alphabet A1 would occur on the marble, and that is possible on marble 1 and marble 4. So out of the 4 marbles, we have 2 such conditions, and thus P of E1 is 1 by 2. Similarly, P of E2 and P of E3 is half. P of E1 intersection E2 is equals to 1 by 4. Same is the case for the other pairs as well. And all three together give probability as 1 by 4. For events E1, E2 and E3, they are pairwise independent because you can see how the math works out. Those three conditions are satisfied. But you can see that P of E1 times P of E2 times P of E3 would give half to the cube, that's 1 by 8, which is not equals to 1 by 4, and thus these events are not mutually independent. Having understood the concept of pairwise and mutual independence and the subtle difference or implication of mutual independence over pairwise independence, however the reverse not being true, let's dive into what is total probability. So let P of Hi be greater than 0 and Hi's constitute a set covering of capital Omega. Here, set covering means that it's a collection of sets such that they are pairwise disjoint events and their unions constitute the whole universal set itself. That is, they entirely cover the universal set. In this figure, you can see how Hi's uncover or let's say exhaust the universal set, and suppose there is a set B within that sample space. We can write B as B intersection H1 union B intersection H2 and so on. Because Hi's are disjoint, all these intersection with B are also disjoint as by definition. So P of B is equals to summation of P of B intersection Hi over all i's, and that is made possible from the axiom 3 that we learned for probability. Thus, using conditional probability, we can write this as P of B equals summation of P of Hi's into probability of B given Hi's, and this formula is popularly known as the total probability of B. However, something to note here is that this is defined only when we have a set of Hi's which are mutually exclusive and mutually exhaustive. By exclusive, we mean that they are disjoint, and by exhaustive, we mean that they cover the whole universal set. So this is the formula that we used to take granted in school. In school, this used to hold valid because we generally used to take only two possibilities that took care of everything. For example, a patient having cancer and not having cancer. So generally, we had such simple examples that it automatically covered the whole universal set. Similarly, we already learned for what is the point number 2, that's pairwise disjoint, and what's point number 3, that comes from the conditional probability. This formula directly extends into what we call the Bayes theorem. So let's get into it. Bayes theorem, for that we need to have probability of B greater than 0 and probability of Hi's also to be greater than 0, and that is because of the conditional probability case. We can write probability of Hi given B as P of Hi intersection B over P of B, and probability of B can be written as the total probability using the above formula. So the final formula comes out to be this, and this we call as the famous Bayes theorem. Bayes theorem has wide applications, and if you are trying to go into the field of machine learning or more deeper into mathematics, you would definitely have to use the Bayes theorem a lot. What's the intuition behind the Bayes theorem itself? So let's take an example. Suppose we want to find out the probability of a person having a disease, given that the report says that the person is positive for that disease. So in this case, let's say event A is lung disease present and event B is that the report is true. So we want to find out P of A given B, right? However, we know that the machine is some X% accurate, which means that we already know P of B given A, that is the probability of the report being positive given that there is lung cancer, and that is X by 100. We also know that P of A is something because we know the population statistics, and thus P of A given B can be found out using the Bayes theorem because we know every probability on the right hand side. This becomes especially useful when we know the effect of A on B and we want to seek the effect of B over A. To sum it all up, we have the following takeaways from this video. First, P of A intersection B is equals to the multiplication of the individual probabilities of A and B for independent events. Second, mutual independence implies pairwise independence. However, the reverse is not true. Thirdly, we came across what total probability is and what's the formula or the intuition behind the Bayes theorem that is an extended version of the total probability. And that is the fourth major insight from this video. Hope this video added some knowledge and value to your foundational understanding of probability. In the next video, we'll move on to understanding what random variables are, which marks the milestone that we are going deeper into the concept of probability and something that is extremely important for modeling purposes and for practical situations. To give two names, it's widely used in machine learning, AI, and supply chain management. If you like the content, don't forget to like the video and subscribe to the channel. Till then, stay safe, stay healthy. Rachit Jain signing off.